Hey everybody, I'm Nick Moore, Director of Product Management for Vanguard Electrification.
And I'm Stephen Avery. I lead the application engineering team for our electrification products at Vanguard.
And we wanted to put something together for our OEMs and people out there. You know, we deal with a wide variety of customers who are looking to electrify pieces of equipment. And capabilities and understanding of what it takes to do that are pretty much all over the map. So we thought it'd be pretty helpful to give an idea of what are some of the key components and ways that you have to look at how to integrate to get the best performance out of a piece of equipment so that your end users get the best experience possible. So what we're going to do here is start by describing what are some of the key parts and pieces that go into building a piece of equipment, and then go through what does it actually take to make sure that they're working together properly. So what it all starts with is a battery. So what we have here is our SI 1.5 swappable Vanguard battery. There's all different types of chemistries, and obviously batteries has been around for a long time. There's lead acid, there were NiCad, nickel metal hydride, all these different types, and really power tools is what people think about a lot. The great thing about lithium is that it gets rid of some of the bad things that people were familiar with back in the day. There's no memory, so really you don't have to worry about trying to discharge it all the way and then charge it back up after that point to make sure that the battery doesn't get a shortened life from mischarging. The life expectancy is so much greater than lead acid and the NiCads and things like that, as well as the battery is a lot lighter than when you compare to lead acid batteries. A piece of equipment that's maybe powered by lead acid batteries, you replace that with lithium, it's going to take up a lot less space and weigh a lot less, so that you're not having to move as heavy of a piece of equipment. Along with that then, when you look at lithium-ion batteries, is all the different cell types that make up the battery itself. So there's cylindrical cells, there's pouch cells, prismatics, all the different chemistries and things like that you're going to hear about. It's really hard to keep it straight, and frankly, it keeps changing all the time. So really what we try to tell people is make sure you're doing your homework to understand, just saying a lithium-ion battery can mean a lot of different things. So you want to do your homework and make sure that you're trying to pick the right battery for what you're trying to do and accomplish with your piece of equipment.
And even within lithium-ion, there's all sorts of chemistries. So there's cell types, the form factor that lithium comes in, but it's also the chemistry in the anode and the cathode that goes along with it.
Yeah. So and as we said, it's kind of evolving pretty quickly. So again, a lot of work goes into making sure that you know what you're getting and what it means. And really, the most important thing that translates to is how safe is this battery going to be. Everyone knows that when something does go wrong with a battery, as the automotive world tries to transition to EVs, anything that does go wrong is typically big news. With all those different types of chemistries and cell types and ways people are making batteries, there's a lot of different ways that they actually configure the cells inside the battery pack that can make a big difference on how it performs, and is it actually the right battery for the right use case. So is it a battery that's made to handle shock and vibration, or is it one that's better being stationary at all times? And then what does that mean for my piece of equipment? Is it made to withstand the elements? What's the IP rating? Is it going to handle being sprayed by a hose or a pressure washer or things like that, and what kind of temperature ranges? So all these different things come into, they matter when you're thinking about what battery is right for my piece of equipment. From there then really is you got to look at how is the battery controlled. So when you get deeper into how does my piece of equipment work, what matters is how is the battery on board going to communicate, or is it going to communicate with the rest of the equipment on board. So typically lithium-ion batteries have what's called a battery management system, or a BMS. It's essentially the onboard computer. Think about it, as like an automotive, that your car has a computer on board that's controlling everything. It's what's making sure that what's going on in the battery is again, ideally keeping the battery safe, and then communicating what's going on with it out to the outside world, so that you can take action and make sure that the piece of equipment is doing what you're expecting it to do based on what the battery is telling it. How that communicates, there's different protocols people use. Typically it's a CAN bus communication for people that do have BMS. Again, you can make a battery without a BMS, but typically it's a CAN bus communication. For instance, we use CAN J1939, a standard protocol. That is really important as we get later into the discussion here around how does it communicate with the different pieces of equipment. Different battery manufacturers have different levels of information that's available to you, what the battery actually gives out, so that you know what's going on inside of it, how much charge is left, as you're getting near any faults or potential shutdowns, things like that, and what can I do with that information. The other big area then that matters, and this is again where the different cell types have a different variety of abilities and what they can do, is where it comes to charging. So for instance, here's an example of our 3,000 watt charger. A lot of battery manufacturers, and what we do is actually you focus on having the battery control and dictate the charge. So you can find, again, there's batteries without a BMS that you're relying on the battery charger or the OEM to pick the right charger that isn't going to overcharge the battery. Overcharging lithium is a bad thing. It's how you shorten life and can eventually get into safety concerns depending on how much you could overcharge your cells. So you want to make sure you understand how is that battery system going to be charged. How am I ensuring that both it's protecting me for life, but also for safety to ensure that I'm getting what I want and that my customers using the piece of equipment are going to get what I want. And again, there's all the different levels that it's really more of a cell dictated of how fast I can charge. So am I sizing the charger to be as fast as possible or to get the longest life possible, and all those different types of factors that come into effect when I'm talking about charging. From there then, think of that as essentially your fuel tank. If you're translating a piece of engine powered equipment, the battery, while it's a whole lot going on, that's essentially your fuel tank. So that's how much energy I have to do work. From there, you actually have to translate that to the spinning shaft of what does the work. So Stephen, I'll let you kick it off. Talk a little bit more about the motor side.
This is an example of our MVG 2200 motor. It is designed primarily for actually spinning what we like to call like a chore motor, and that's a chore motor would be something that's actually doing work on the application. So not so much a traction motor where you're driving, starting, or moving a piece of equipment. This is meant to be kind of like spinning either like a blade on a lawnmower or possibly a pump or some other sort of piece of an application that's actually doing the work or the job that you need to get done. So we could talk about how the motor, these are brushless DC motors, so you don't just give it DC power from the battery. That's more part of like a brushed DC motor, which the industry is kind of getting away from because they're not as efficient, as well as it's harder to get the control you want over the speed and the torque that you want for the application. So because those brushed DC motors, the speed is just a function of the voltage you give it, versus we actually utilize the motor controller where we actually give the DC power from the battery to the motor controller, and then the three phases that go to the motor go to the battery using, in this case, this Anderson connector. But there's also data here, so we can communicate. We will get the Hall effect speed sensors, so we know how fast the motor's spinning to the motor controller, and then temperature as well. And the motor controller can also talk to the battery via CAN bus, so that the motor doesn't use too much battery current and overload the battery, but also just so that everybody's on board. So if you utilize like a vehicle controller with multiple motors, you can command multiple motors to work in harmony to each other.
I think one thing worth noting, people will hear them also called inverters because it is inverting the energy. So motor controller, motor inverter are synonymous in this case.
Right, you're taking that DC power and you're making it, oscillate. So inverting is proper. When you're also picking a motor, it's also important that no two motors are necessarily exactly the same. You want different motors for different applications. We could talk about efficiencies, and you can look up plots for each battery. It's going to show you like torque on the y-axis and speed on the other side, and you're going to have multiple curves of what your efficiency for that motor is. Because speed times torque equals power in a motor, and then so you need to size the power needs you need, the torque you need, and the speed you need, and you're trying to find a motor that hits that efficiency band, because the more efficient your motor is for your application, the better your range is with the battery. Because if you have, say, 10 kilowatt hours of power, if you're a 50% efficient motor, which would be really bad, you could go, half as far as if you had a theoretical 100% efficiency motor.
Yeah, I think it's worth noting too in there that, so what happens when you're not in the proper efficiency curve of a motor? You generally are generating heat,
Yeah.
which is obviously never a good thing to be wasting. You're both wasting the energy, but then also you're degrading the life of the motor more quickly.
Right. So you need the battery, you need a motor, but you also need the motor controller in between, and they all need to be in the right voltage, and they also need to be able to talk to each other when necessary.
So you made a comment about, lots of pieces of equipment are requiring multiple motors to do work. So let's say I'm driving wheels as well as I'm spinning, a blade or spinning a pump or moving an arm of some sort. So how do I manage all that? That's where the vehicle control module comes in. So VCM, some people say vehicle control unit. So
VCU, VCM.
Yeah, a lot of these synonymous things. So don't need people thinking that they're all different components. But basically, what this is another, essentially computer on board. The main goal of this is to kind of set the hierarchy of how do I know how much energy from the battery to give to which controller to drive which motors, and how does it all work properly. So it really becomes kind of the conductor of how the piece of equipment works, and is what spreads the energy around to make it as efficient as possible, a piece of equipment, to do a lot of the sequencing of how is it going to start up, how is it going to shut down, things like that. So again, essentially, if you're doing more than one motor on a piece of equipment, this becomes a must-have, so that you're not, otherwise you're just kind of just subject to where's the energy going to go, and each motor controller can be calling for different things based on what's going on.
Correct. Yeah. And leading up to that is, if you want to take out that little guy, in order to tell a motor how fast to go, there's a throttle control. So there's different ways to do that. So maybe if you're like an autonomous piece of equipment, you don't have a throttle, you just have the computer that has all the sensors with the input going in that tells the motors what to do. But if you have a human operating the piece of equipment, they need to have an input to tell you how fast you want to be driving. Think of it as like the accelerator in your car. That's what the throttle is. And what's pretty typical for throttles is either a CAN-based one, so the throttle sends a CAN command, or a 0 to 5 analog signal. I believe this one is an analog one. And we're able to use either a vehicle control system where the throttle goes to the vehicle controller, which then tells the different motors to spin at the right speed, or if you just have a one motor application, you could actually have it wired straight to the motor controller, and then that motor controller tells the motor how to spin at the desired speed.
So another way of kind of accomplishing that we see a lot is typically if people are electrifying a piece of equipment that wasn't electrified before, you want to put some of the cool factor in. So typically what that means is I want to have a nice digital display. That typically gives you the capability of taking a lot of that. So instead of having an actual mechanical lever to control the speed, I can do it with touch buttons on the display. As we talked about what gets communicated, the display is what allows you to give the consumer, the end user, as much or as little of the information that may be beneficial or just interesting to them as they're using the piece of equipment.
And if you just have a set speed where maybe you have a simple application like a grinder or something where you always just want it running at the same speed every time, you could just use a switch that operates as the throttle, and it's basically binary off or on, but it's sending the signal to go to your target speed.
Yeah, so again, all these different components, it's not that every application needs them all. It really is what am I trying to accomplish, or how easy or difficult of a use case do I have? How many different functions am I looking to replace or to create in a piece of equipment to do different work? Or to your last example of it just needs to turn on and off, and I can just have an on-off switch.
Yeah, all these pieces are just tools in a toolbox, to use a metaphor, and it really comes down to your specific application and how you want it to work. And it allows you to be a little creative in the engineering world of how you actually want to make everything work. And you can add complexity, you can make it simple. The benefit of this complexity is that you can fine-tune it exactly to give it the personality that you want for your application, rather than just kind of a static feeling piece of equipment. So these are all things that my team at the Power Application Center works with our customers to help guide that, especially if they're new to electrification, because a lot of people don't even realize that you need like a inverter motor controller to spin the motor.
Yeah, on top of that too, I mean, when you look at, you could have two identical pieces of equipment with all the exact same components, and they could act completely differently and give very different performance, because it all comes into that, how do you decide, you know, what is my ramp speed and what speed do I actually operate at, and what kind of user input am I giving to actually change and do things differently. And again, that's what gives kind of that feel or personality to the piece of equipment.
Yeah, and you mentioned earlier how a lot of these things are just details you need to look for. It's not necessarily one way is better than the other. And one of those are just like, even with CAN bus, there's different protocols for CAN bus. In the off-highway market or industry, there's a lot of standardization going around the J1939 standard. That's what we utilize. But even beyond that, even if you have that communication protocol saying what all the CAN messages mean, you also have to make sure you're running at the same baud rate, which is just basically the fancy way of saying how fast the messages are being sent. So our Vanguard products for our electrification utilizes 500 kilobits per second. And what's interesting is you can actually mix like CAN open with J1939 CAN messages, but they have to be at the same baud rate. You cannot have two different baud rates on the same bus. But there are pieces of equipment that can have multiple CAN buses on it that could also do translation. So maybe some components are on 250 kilobits per second, but some components are on 500. So that's all part of your vehicle or systems architecture. So it's just another detail to consider. So it's worth mentioning.
Yeah, and that's where, again, where it becomes really important that as an OEM, you have someone on your team or you have the right partners that help make sure all that stuff works together. You know, we've had experiences where a customer comes and says, well, I have this, you know, motor and controller already picked out. I want to use that. I want to use it with your battery. Well, sometimes you can't make the components talk together properly without having to buy a separate piece of equipment or doing a whole bunch of programming. You need to understand how important it is for these items to talk together, especially when it's part of your safety circuit or control circuit of, okay, this is what's going to make the unit turn on and do work or not, or be consistent in how it operates. And that becomes really important to the end users so that they get a repeatable, safe experience when they're interacting with these pieces of equipment.
Absolutely.
One other thing that I think is really important as we talk about, you know, kind of the putting it all together is what does the piece of equipment do if I'm getting near my low state of charge? I mentioned earlier if the battery is, you know, nearing a fault or things like that. That's where the more of the communication you pull together, we always say our goal is that a piece of equipment never shuts off and a customer not know why. So you want to make sure that there's a way of alerting someone of, hey, I'm getting, you know, near a temperature limit, so I need to derate. You can program all that type of stuff in. You can make it seamless, so they don't even need to know that the piece of equipment handles it of, okay, I'm overloading the system. I'm going to start to work slower or no longer have this motor work, but the other ones can continue to work. All these different scenarios that you can work through, that by having that level of intelligence, and by ensuring I have a BMS on the battery that's communicating where the battery state is at, becomes a big benefit to ensure that you're giving the users that best experience as possible.
Absolutely, and you're talking about the you know, derating or controlling the power output, but that's also within the bounds of having to spec out the application correctly to begin with to make sure all your components are able to handle the power requirements you have. So making sure your motor controller can give the amount of current it needs to, the battery can, and the motor can all take that power. And that's understanding the application, and that a lot of times that's easier said than done, especially if you're coming from an engine-powered application and you're now repowering it. Because of course, like a horsepower of power is equivalent in a different, you know, unit than kilowatt. So kilowatt basically is the same thing as a horsepower, just not mathematically, right? Different scale. But you can't just assume, well, if I'm taking a 5 horsepower engine off the application, that you're going to do 5 horsepower the whole time, because usually an engine application you're not using all 5 horsepower the entire time, you're using a percentage of that. So understanding that is important, as well as what the duty cycle is. So are you turning on the application, so are you using 5 kilowatts for 30% of the time, you're on for 30% and then you're off for 70%? What is the environment that's running in, the ambient temperatures? All factors to consider. as well as you can take the collection. So if you're doing 10 kilowatts for an hour, on average 10 kilowatts, that's going to be 10 kilowatt hours. Hard math there, doing mental math. But that's important to know for the energy that you need for the system. But you need that energy in the battery, but you also need a system that's able to provide that amount of power consistently. So we talk about things like peak power, because maybe you do an average of 10 kilowatts, but you need 20 kilowatts of peak power because the application accelerates. So we're talking about peak versus continuous, all things that we need to consider.
Yeah, cool things about lithium as you compare it to either an engine or even like a lead acid system, if you're making a conversion, is lithium has the ability to give you a peak for a short time that's quite a bit higher than typically an engine will, or definitely what lead acid will. So you're able to do things where maybe I don't need to put as much installed battery on my piece of equipment because I have a really high starting load, but then I run at a really low load. On an engine, you're gonna, let's say I need 40 horsepower to start the load, but then I'm actually running consistently at 10, you're going to put a 40 horsepower engine on it because I have to get that starting load. On the battery, you can do it quite a bit lower because it has the ability to take that peak for a short time. And that's the type of stuff that, again, working with your engineering group is really important, because lots of times we get asked, how long will this run, or how much battery do I need? The answer, unfortunately, is always it depends, because it's what is my actual continuous rate versus the peaks and all that. So that's where, again, you have to get into that level of detail to really understand it. I think one of the big tools that you guys utilize that really helps is we try to tell OEMs is if you don't truly know, let's build a prototype, because once you have these smart components on board, all you have to do is collect the CAN data and you quickly see exactly what's happening. That then you can do the calculations of, okay, based on this load, I want to get this much runtime, this is how much battery I need to put on board.
Yeah, and it's usually easier to over-spec that first prototype so that you have too much battery power, and then you understand how much kilowatt hours do I actually need to get the job done on a daily basis. You also mentioned, we were talking about engine conversions, but also when it comes from like a lead acid conversion, maybe you have a piece of equipment that was powered with lead acid. It's a little bit easier because you're already going from an electrical system, especially if you're already in the same voltage range. But you do have to consider things such as you don't necessarily need the same amount of amp hours or kilowatt hours of a lithium battery as you do lead acid, because lead acid doesn't have as good of a depth of discharge. So you can use a greater range of the capacity of the battery when it's lithium over and over again, especially at higher loads. The battery is able to give you that much power through its range, versus a lead acid battery is going to have issues. Lead acid is also a higher resistant battery, so we've had fun sometimes where we took off a lead acid battery and we kept the controls. We didn't reprogram the controls, and since they were programmed for a lead acid battery, the proportional gain was cranked in it, and so when you put a lithium battery with a lower resistance in it, the motor really took off. So that's pretty rare occurrence. Usually the controls are better tuned, but it is, once again, just another thing to think about.
Not as easy as just replace the battery and go.
Yeah, sometimes it is, but sometimes it isn't. It's just a possibility.
Yeah. So I think worth ending here. We have a demonstrator to just kind of show, here's a mock-up of what would a single motor controller with our swappable battery look like, and it's got a throttle on board that we can turn the motor on and off. This could very well be, think of it replacing your single cylinder horizontal shaft engine on a construction piece of equipment or something like that. So, just to give the idea of, okay, you bolt all these components together and I can get that same functionality of an engine or things like that, and all the different type of work you can do from it.
All right, so here we have an example of what I would call kind of like a power head replacement. This is actually something we've created to replace an engine on a piece of equipment such as a trowel. So what we actually have is mounting points that utilize what engines we're using, the engine that was on the application, and you can see that we have a motor with a shaft coming out here, and that allows us to interface with the pulleys that were on the application beforehand. Right here with this yellow latch on it, this is the dock for our SI 1.5 swappable lithium-ion battery. So this is the piece of equipment that our customers install on the application so that we're able to just slide the battery on, just like this. And it's able to power the application. So I'm going to show some other components here. So if we spin this around, you can kind of see through the protective mesh. There's a motor in there. And on the back side here, we have a plastic protective cover. And underneath that cover is the motor controller. So that's where the battery is connected to the motor controller, and the motor controller is connected to the motor. Some other components here, these are things that are very much optional, or in our case we use for data collection and testing, but might not be on an application. This here is a CAN data logger. It's very cost effective. We utilize a lot of these in our shop because we're able to put one of these small guys on the application, send the application out in the field, and just have people who actually use the equipment on a daily basis test with it, and we're able to then grab that data and understand how well the application met the needs of the user. Here we have something called the DC-DC converter. In this case, we have a 48-volt battery. There's some components like the data logger that needs 12 volts, so we are taking that 48 volts and converting it to 12 volts. So in this case, we're only using it to power the data logger, but other applications, you might have some 12-volt components or lower voltage components that need to be powered, so you might actually have one of these in the end unit. And I just wanted to show you then, and on top of that, we talked earlier about the throttle. So this is just an example of an off-the-shelf throttle, and we're able to turn on the battery. With this switch, we're able to turn on the throttle this way, and then if we just spin the throttle, the motor spins. So that's all part of it. So the throttle is communicating with the motor controller, and the motor controller spins the motor. So that's an example of really an example of a single motor system.
So with that, really what we want to do is ensure that, if you're an OEM looking to electrify a piece of equipment, we're here to help. We have a whole department focused on helping our OEMs work through these technical details. So if you go to vanguardpower.com, we have a little sheet you can fill out to say what you're interested in, and we'll contact you that way. If you're an end user, you can go to the site and just learn more about all the components that we have available. But again, really, we'd love to work with as many people as possible to help electrify as many pieces of equipment as possible, and keep this type of equipment growing in the marketplace and get more of it to be available.